Hello, students. Okay, so lately we have been talking about heating curves and cooling curves and what happens at the particle level when heat is added to the system and heat is removed from the system. So something to keep in mind is to remember that energy is constantly being added. Heat might not be being added, but energy is constantly being added. Sorry for my not so straight line. But if you remember, we have a period where we are entirely solid. Then we have a period where we have our phase change that's occurring. Then we're entirely liquid, phase change, and then entirely gas. And that's where we stopped. We stopped at the gas point. And so if you remember, we labeled this A, B, C, D, E, and F. So here we have as time went on, but it's also as we add energy. So energy is constantly being added. I know that during the phase change times, the temperature isn't changing, but that's because the energy is going into spacing out those particles into the phase change itself. So that is something very important to make sure you know, is that it's on our x-axis as time increases, but it's also as energy is being added from the system, added to the system, in our heating curve. Now in our cooling curve, it's as energy is being removed from the system. So that would be a negative energy if this were a cooling curve. And so then here we have our temperature, which remember is in degrees Celsius. So if you remember, when we were talking in our last unit, we know that there are some things that impact what actually causes the energy to change. Sorry, just a second. I'm bringing something up so that way I can keep myself on track, because you know me, I love to get off task sometimes. And so when we're talking about heat, we're going to start talking about heat. So we were talking about energy being added and removed from the system. Well, now we're going to specifically talk about heat. And so the first thing we need to answer is, what is heat? And so heat is really our total energy. And so total energy is usually E tot. And so what do we mean by total energy? Well, we mean our kinetic energy plus our potential energy, which is our phase energy. So heat is the total energy. It's the energy that's being added to the system. And so in order to look at this, we're going to talk about the variable. So heat is our variable of Q. And in this case, we're not going to talk about just heat, but we're going to talk about the change in heat, or heating. So heating is going to be delta Q. So what does that mean? What would cooling be? If I were removing energy from the system, what would cooling be? And so we should be thinking that cooling would then be negative change in heat. So it's when our heat decreases. We talked about this the other day. There's really no such thing as cold. It's really heat and less heat. It's heat being added to the system and heat being removed from the system. So when we say something is heating, we're saying that we're adding heat to the system. When we're cooling, that means we're removing heat from the system. And heat is just energy. It's our total energy. So that's important to keep in mind. So Q is our heat. Delta Q is heating. As far as units, we're going to get to units in just a second. So let's look at something else first. So the things that impact our heating, the things that impact our observations that we've been seeing, we've talked about this. We talked about that with particles, mass plays a role. And so in this case, keep in mind that we're talking about the same particle. So let's say I'm talking about aluminum. When I talk about aluminum, my particles are all the same. Whether it's hot aluminum or cold aluminum, it's still aluminum. And so when we talk about mass in this case, we're not talking about particle mass, we're talking about our system mass. So So we're talking about increasing the mass of the system, adding more or removing the particles. So adding or removing the same type of particles, not necessarily the mass of the particles themselves. And so when we talk about mass, let's talk about increasing mass. This is going to look very familiar to our last unit. It's almost like I was trying to set you up to be prepared for this. I know it's crazy, right? I actually teach you things for a reason. So as we increase our mass, that means that our number of particles are also increasing. Remember, it's not the mass of the particles, it's the number of the particles. So if we were drawing this in a particle diagram, we wouldn't be changing the size of the particles, we'd be changing the amount of particles. So maybe I go from 5 particles to 10 particles when we're talking about mass here. And so since I'm increasing that number of particles, well, things are, I have more particles, so that means that I have more collisions. And as I have more collisions, that means I'm going to have more energy, so I'm going to have a higher change in my heat. Okay? So hopefully that makes sense. Now, when we're talking about mass, our units for mass, hopefully you all know this, even if you didn't say it, but our units for mass are going to be grams. And our variable, because we're going to start doing some equations, we're going to start doing some calculations. So our variable is m. And so basically what we said here, let me use a different color. What color do I want to use? I'm feeling kind of blue for mass today. So on our graph, what we have is our mass is going to be what we're changing. So this is my independent variable, and my dependent is going to be the change in heat. Heat, we're going to use a measurement of joules. So energy is measured in joules, which means I can go ahead and add what our units are for Q. Yep, so Q, I had my variable for Q, so let's do units are going to be the joule, okay? And so as my mass increases, then that means I'm going to have an increase in my amount of energy, okay? So now let's look at what else impacts the amount of energy. So mass does, but what's the other thing that we talked about? So if you remember, almost like we planned for it in Unit 3, we could change the mass or we could change our temperature. So remember that our temperature was the average kinetic energy. And so our variable that we're going to use to represent temperature is a capital T. Yes, it must be a capital T. Why? Because that's what it is. And so then our units, I'm not going to put this right there. I'm going to leave some room for when I do my graph here in just a second. So variable units are going to be in degrees Celsius, no Fahrenheit. We're going to talk about Celsius here, okay? And so then as we have our temperature increase, and this part you should be familiar with, our kinetic energy is going to increase. Now, we're not talking about, we say kinetic energy, we're not talking about mass, because as we said up above, our mass of our particles is the same. And so we're focusing on the kinetic energy. And so since we know that the mass isn't having an impact, we know that that means that we have a higher velocity. Because of the higher temperature, we have higher average kinetic energy, which means higher velocity. And then we have a higher number and force of collisions. Oopsie. So we have a higher number and force of collisions. And since we have a higher number and force of collisions, that means that my overall energy is going to increase. So we have a higher change in heat. So those should be familiar to us so far. And so then when we talk about our energy, once again, we're changing the temperature. So we're talking about our temperature in degrees Celsius, and then we're going to talk about the impact of it on our total energy or our heat. And so as our temperature increases, so is our total energy. So once again, this should be pretty much review from last unit. Nothing too terribly new right now. However, in our last unit, we did compare the difference between different materials. For example, we compared aluminum to copper, and we sat there and said that, one might be hotter than another. Well, in this case, since we're talking about two different materials, then that means there's something different about the different materials. And the different thing about the different materials is referred to as its specific heat, and that's how much, that's its ability to absorb energy. Its ability for that change in energy to occur. We know that sometimes, here, let me write this down first, and then we'll go over that, my analogy, my example. Is this color going to be able to be seen? So 3, yep. So 3 is going to be called our specific heat, specific heat capacity. And so with our specific heat capacity, our variable is going to be a lowercase c. It needs to be a lowercase c. Remember, for temperature, it's going to be degrees C. That's a capital C for Celsius. This is going to be a lowercase c. And so with our lowercase c, our specific heat capacity, our units, which will make sense in a minute, are going to be joules per grams degrees Celsius. Okay? And so then with this is, for example, let's say that I put aluminum and copper on a hot plate. Most of you probably know, so aluminum, like our aluminum foil, if you put aluminum foil on a hot plate along with copper is a good conductor of energy. And so our copper is going to feel, our copper is going to be a different temperature than what our aluminum is. It's going to transfer that energy differently. And so when we look at this, we're going to have our type of material, in this case a metal. So our type of substance. And because of our type of substance, it's going to have a different particle mass. So now for number 3, remember 1 and 2, we were talking about the same particle mass. So we're talking about the difference in system mass in 1 and 2. Well, 3 is different. Specific heat capacity is now talking about the particle mass. The particle mass is different. And so since our particle mass is different, that means that our spacing is going to be different, which means our potential energy. Remember, our heat, delta Q, was dependent on the kinetic energy and the phase energy. The kinetic energy is related to mass and temperature. That's what helps to change the velocity, the average kinetic energy. Well, specific heat capacity is talking about our phase energy. It's talking about those space between those particles. So since it's talking about particle mass, then it's really coming down to particle spacing. And so when we talk about this, for example, if I have aluminum and I have copper, we know that aluminum is less dense than copper. So there's going to be more space between the particles than there is in copper. So for example, if I'm comparing aluminum to copper, then I know that with my copper, I would have a higher particle mass. And remember, how can we determine the particle mass? We look on the periodic table. And so on the periodic table, everybody flip to your periodic table real quick. I'll give you a couple seconds. And so look at your copper compared to your aluminum. you should see that the copper has a much higher particle mass. So our particle mass is higher. And remember what we said, the impact of particle mass being higher on our velocity. Higher particle mass, lower velocity. Once again, it's almost like we were trying to prepare you for something. And so since it has a lower velocity, that means we have a lower number and force of collisions. Which means we're going to have a higher density, which means we will have a smaller, actually I guess I should probably write that, sorry, which means we're going to have less spacing between particles, which means a higher density, which means we are going to have a lower change in heat, a lower total energy change. And so then with this, if we were to draw a graph, we have our delta Q on the side, just like before. But in this case, since we're talking about particle mass, velocity, number of collisions, we're talking about mass and temperature. Now those both have a role. The mass of the particles and the temperature of the particles have a role to play here. And so we're going to be talking about our grams degrees Celsius. And so now hopefully, if you look at your graph, remember the y goes over the x, this is why it shows you that our specific heat capacity, our units, are joules over grams degrees Celsius, because that's going to be our slope. And so our slope, our aluminum's actually going to have a steeper slope than our copper, because as we said, higher density means a lower change in energy. So normally when you're used to seeing these two, you would have said that the slope was greater, but that's because you'd be thinking about density. So the greater the density, the lower the change in heat, okay? So that's something to kind of get straight in your head. It's going to take a little bit of practice. That's going to be a common error that you guys make on homeworks and quizzes and whatnot until we get this a little bit more solidified in our brain. And so then with this, what we've been talking about then is when we have our heat, we're talking about three things. Heat being the total change in energy, or the total energy. When we talk about the change in that total energy, there's three things that go into it. The two things that go into the kinetic energy specifically, mass and temperature, and then the phase energy, the spacing, the density, which is specific heat capacity. These three things play a role in the total energy change. And so we get kind of a formula. With our formula, we get that our total energy, Q, is equal to the mass times the change in temperature times the specific heat capacity. Now, when I talk change in temperature is going to be when you take your final temperature and subtract your initial temperature. Okay, that's important because that's going to give us a positive or a negative. If it's a positive, then that means that our final temperature was greater than our initial temperature, so that would mean that the temperature increased. If our final temperature is lower than our initial temperature, then it will be negative, and that tells us to decrease. So now you guys kind of see how why in earlier units, when we did our percent error, I didn't have you do the absolute value. I know some other classes did that. I had you keep the numbers as positive or negative so you could get into the practice of it meaning an increase or a decrease, because I knew it would play a role here, and hopefully that would keep it a little bit steadier. So now that we've done that, let's do an example. And so with the example that we're going to do, it's going to be a little bit trickier of an example, but that's okay. I'd rather do a tricky example while you're doing it with me rather than send you out into the wild on your own after all we did was something simple. So when I'm looking at this, we're going to use our ratios again. I know it's terrible. It's a horrible, terrible thing. But let's say that I have a pot of water. And so with my pot of water. It's placed on a burner at medium heat and warmed. And so as it's warmed, I've got my energy bar chart. Okay. This is why we were doing the energy bar charts. For some problems, you'll get them where they don't have an energy bar chart. If it helps you to draw an energy bar chart to visualize what's happening to the energy, please go ahead and do so. So we have our water that is set on the burner. So this is my water. I guess I should make that bigger so I can write it inside, because that's what I've been doing in class. So there we go, water. And then I'm going to be talking about two different systems here. I'm going to be talking about the water as a system, and I'm going to be talking about the pot as a system. I'm going to consider the energy transfer between both systems. Or burner, sorry, not the pot. I said pot, I meant burner. Okay, so our pot and our burner. I apologize for my messiness, but you know, these things happen. So then with this, when we have the water started at a lower temperature. Remember, the amount of bars is kind of arbitrary for that, but the phase is important. So my phase is at a 2. Well, while it's on the burner, it starts to get warm. I'm going to say that warm in this case is 4 bars. And so now with my phase energy, actually, no, whatever. With my phase energy didn't change. It's still a liquid. So this tells me that my water has gained 1 bar, 2 bars of energy, because I went from 4 bars to 1, 2, 3, 4, 5, 6 bars. And so to get from 4 to 6, I had to add 2 bars of energy. Well, my burner starts out as pretty darn hot, right? So I'm going to say that my burner starts out at 1, 2, 3, 4, 5. Phase energy, it's a solid. Well, afterwards, my phase energy is also a solid. However, I need to figure out what energy. And I know we get confused because a lot of times we'll sit there and say, oh, well, it stays the same temperature, so the kinetic energy is the same. But it's not. It stays the same temperature because it's being supplied with constant energy. But that doesn't mean that energy still isn't being transferred. The reason we have to supply it with energy is because energy is constantly leaving the system. We need to replenish that energy. And so why is energy leaving that system? Well, for our water had to get that energy from somewhere. Remember, energy can be transferred, but it's not created or destroyed. So in order to get 2 bars of energy transferred to the water, that means that it had to come from the burner. So we know that from the burner, we had to have lost 2 bars of energy. Well, I know I didn't lose it from my phase because it's still a solid. So that means I had to lose it from my kinetic energy. So I went from 5 bars of kinetic energy to 3 bars of kinetic energy. Okay, so we have to keep it the same. And so now let's say that approximately 5,207 joules of energy of heat energy was added to the water. And so now I want to know how many joules left the burner. And this is actually pretty easy. You're going to insist on making it tricky because you think that since I gave you equations and talked about that stuff that it's going to be tricky. But remember what I just said. So 5,207 joules of heat were added to the water. So this plus 2 bars is representing 5,207 joules. So if that's how much was added from the water, how much was removed from the burner? And as we said, since it's 2 bars from the burner, then that means that the amount that had to have left from the burner has to equal the amount that was added to the water. So there was 5,207 joules removed from the burner. Okay, so now that we did that, now let's actually go into a little bit trickier of a one. So now what I want to look at is, let's say that the water starts out at 18 degrees Celsius. So my water initial is going to be 18 degrees Celsius. And you know what, let's not do W because W is just weird. I don't know, maybe it's just me, but H2O. So my water, the initial of my water is 18 degrees Celsius. And after I leave it on the burner for a little bit of time, my water heats up. So my final water is going to be, I don't know, let's say 65 degrees Celsius. And so I want to know, how much water do I have? So I want to know, what's the mass of water? Well, something that I didn't tell you is that the specific heat capacity of water, now it depends on if you're talking about water as a gas, a liquid, or a solid. And so in this case, we're talking about water as a liquid. So the specific heat capacity of liquid water, that's a cursive L. So the heat capacity of liquid water is 4.18 joules grams degrees Celsius. Okay? And what that really means is that it takes 4.18 joules to raise the temperature of water, to raise 1 gram of water 1 degree Celsius. We'll get into that when I get back. So we'll get into that a little bit more later. But here's what I have. And so remember that what I'm really starting with is going to be my joules. I know how many joules were added to this water, so this is a continuation of the previous problem. I guess I should have said that, I apologize. We're going to continue the previous problem and say that in the previous problem, this is how much the water changed when I added that much energy. And so now our given is really our energy. So I have 5,207 joules. Okay. And so now I also have my specific heat capacity, because I need to get rid of these joules. And so to get rid of joules, I need to use my specific heat capacity, and I need joules to be on the bottom. So that means it's going to be 4.18 joules on the bottom. And on the top, this is my 1, so it's 1 gram times 1 degree Celsius. Okay? Then my joules cross out. I know, it's almost like I did this for a reason. Oh, wow, I keep saying that a lot, don't I? So then, when I look at this, now I need to get rid of my degree Celsius. Well, good news, I have my degree Celsius where I'm trying to determine the change in my energy. So in this case, it's going to be 1 on top. And then I need my final minus my initial. So 65 degrees Celsius minus 18 degrees Celsius. Yes, you must put your units with it the whole time. Okay? And so since this is going to end up reducing. And so we're going to end up getting 47. And it's a positive number because heat was added to the system. Okay? So that'll end up being 47 degrees Celsius. No matter how you type it into your calculator, that's fine. But the important thing is that our degrees Celsius will cancel out. Okay? So those two will cross out with that. And then we'll end with our grams, which is what we want. So all we have to do is type it into our calculator. And when we type it into our calculator, let me go ahead and type it in. So 5207. You guys should be doing this while I'm talking about it. Divided by 4.18. Divided by 47. And we should get 26.5 grams. Okay? So that's how we do those problems. Give you a second to catch up. So what if I asked you to determine the heat capacity of the burner? And this is where I'm not quite sure time-wise, if you're watching this in class, if you have time, you can finish this later if there's not time. But I want to talk about the burner. So if the burner had a mass of 450 grams, and the temperature, so this is our change in temperature decreased by 25 degrees Celsius. Keep in mind it decreased, so what does that mean? It means it has to be a negative 25 degrees Celsius. What was the specific heat capacity of the burner? And so once again, we're going to start with the energy. We know how much energy we had because we know that it lost 5,207 joules of energy. But since it lost it, it has to be a negative. Now I'm going to try to figure out the specific heat capacity. And so I know that my specific heat capacity is joules over grams degrees Celsius. So in this case, I don't want to cross off those joules. Instead, I want to end with joules on top and grams degrees Celsius on bottom. Well, I have my grams and I have my degrees Celsius. So I'm going to say that I have 1 over 450 grams times 1 over, don't forget this is a negative 25. We lost energy from the system. And then I go ahead and I plug that into my calculator because I'm going to have my joules, grams, degrees Celsius. Follow your units. That's why we do it this way. I know you guys keep wanting to depend on formulas, but by following your units, it sets you up to make sure that you actually set it up correctly. So I'm going to take 5,207, divide it by 450, and then divide it by a negative 25. And when I do that, I get that my specific heat is 0.46 joules, grams, degrees Celsius. Okay? So that's how you calculate using your heat energy, mass, change in temperature, and your specific heat.